Good morning. My name is Mikołaj Baranowski, and I would like to welcome you to the first webinar from the cycle, from an unpaired electron to an image. I hope you will find this presentation interesting. I will talk about the development of the radio spectroscopy techniques, and I will focus mostly on the EPR and, of course, its motivations. I will talk about the history of the EPR, how it's developed through times, and what obstacles must have been overcome to create the commercially used imager. Development of medical imaging techniques is an optimal combination of multiple fields. First of all, its instrumental development requires physical, chemical, medical knowledge, and of course, technologies. Development of a contrast agent and the pharmacokinetic procedure. Development of experimental modes requires medical, veterinary, and pharmacological approach. Multimodal analysis with multiple perspectives will be also very important for finding a solution from a complex system. I will briefly discuss the future directions. Transitional of preclinical multimodal imaging techniques combining PAT, EPRI, and MRI would be useful to monitor abnormal cells microenvironments such as tumor hypoxia, oxygenability, redox status, and glycometabolism. Why it is important? Because it has been known for over 100 years that the tumor hypoxia is universal characteristics of solid tumor. It increased the effectiveness of radiation therapy. Today, I will focus mostly on the low-frequency EPR for biomedical research. The sensitivity of the EPR has increased in consecutive steps from around 200 in early 1970s up to 3000 with the new microwave sources and new very high-quality cavities. Some necessary microwave and radio frequency components were not available on the market and had to be developed and produced by the company itself. And first, the minimum theory. The EPR technique detects molecular species with one of the more unpaired electrons, paramagnetic complex, radical, lattice defects, or etc. On this slide, the relation between the magnetic fields and frequency has been shown. The gamma is an electron gyromagnetic ratio. For example, the proton gyromagnetic ratio is 3 orders of magnitude smaller than the gyromagnetic ratio for the electron. From this equation, it follows that the physical conditions must meet with the help of electronics. So we have to place a sample containing unpaired electrons in external magnetic field of the certain value. To register the absorption signal, we need to create a fast varying magnetic fields perpendicular to the constant field. Today I will focus on the continuous wave mode, where we sweep the frequency of the RF source and record the EPR signal. The width of the register curve depends on the physical parameters of the sample. We can also reverse the situation and log the frequency and sweep the magnetic field. In continuous wave mode, the signal is recorded in the presence of RF excitation. That's why it's necessary, it's crucial to use the high frequency sources with a little phase and amplitude noise, little as possible. It all started with Professor Zawoyski in 1944, when he discovered the EPR phenomenon on first work entitled Spin Magnetic Resonance in Paramagnetic. And the paper was published in 1945 in English. The image at the right shows the reconstructed apparatus on which the first EPR signal were recorded at the frequency of 133 MHz. It should be noted that the EPR belongs to the family of magnetic resonance. Discoveries and techniques were mutually adopted and used as electronics technology and circuit development. Electron paramagnetic resonance depends on atom possessing an unpaired electron, thereby limiting the range of its application,
but making it useful for detection and identification of the free radicals. Zavoyski might also have been the first to see the NMR signal, but he did not follow it up, at least not with a publication. On this slide, I mentioned the key events, the milestones in development of both radiospectroscopic techniques, EPR and NMR. In 1936, Gorter reported the negative results of an attempt to detect the nuclear magnetic spins. However, this result did not discourage other researchers who nevertheless continued their research. And in 1939, Rabi reported observing magnetic resonance in molecular beams. It should be mentioned that in 1941, Zavoyski observed proton magnetic resonance. However, the NMR signals were not reproducible. What was next? In 1946 was a very prolific time for the development of magnetic spectroscopy techniques. The development of NMR spectroscopy technique was one of the most important factors in advancement of medicine in 20th century. Parcel and Bloch in 1952 were Nobel Prize laureates in the field of physics, developing new method of precise measurement of nuclear magnetism and the discoveries made thanks to them. In the middle part of the slide, the first NML signal has been presented. The experience gained while working on the radiolocation techniques turned out to be extremely important in the future development of the radiospectroscopy devices. Faster development of signal detection techniques has been made possible thanks to the invention of the transistor. It is considered a breakthrough in electronics as it replaced the large, unreliable and energy-consuming electron tubes, giving the rise to an increasing the miniaturization of the electronics instruments and devices, especially since the lower power consumption allowed to reduce the passive elements cooperating with the transistor. In integrated circuits with the high scale of integration, for example, the microcontrollers and microprocessors, the number of exceed to 1 billion those days. In 1973, Lauterbur's short paper published in Nature presents the concept of using NMR for imaging. This is a turning point that underpins almost all of the today commercially available magnetic resonance imaging techniques. Much of today's equipment, especially based on low-frequency EPR, still uses the general principle developed by Lauterbur. In 1975, in vivo experiment on rats was performed. The EPR signal observed with the helix immersed in the solution of temple. The in vivo detectability with the helix was more than one order of magnitude worse than this in the in vivo case. Author described the potential solution, and this solution could be, this is a citation from the paper, this can be probably be improved through the use of time averaging computer. In 1975, Koch communication describes the EPR imaging experiment carried out on the diamonds with the demonstrate that it is possible to map the distribution of the paramagnetic centers in such a system with a potential resolution of order of microns. First, EPR biological specimen imaging were accomplished at L-band frequency. L-band frequency, I mean, this is from this paper, it was about 1.4 to 1.9 gigahertz, and it was done with a single-turn flat lap surface coil. One-dimensional imaging spectra were diagnostic on the capillary structure of the long-term stability. The peak-to-peak splitting was about 5.9 Gauss, which corresponds to 3 millimeter separation, I mean center to center, between the two capillaries. The author estimated that the resolution of 0.3 millimeter is possible. The authors described that it is apparent that the L-band EPR imaging is feasible for aqueous materials and that the prototype system described here in this paper can provide the valuable information in future in vivo experiments. To obtain microenvironment parameters such as PO2, pH, redox state, or PI, the dedicated spin probe were synthesized. The shape of the recorded spectrum depends on the parameter of the microenvironment. As you can see in the animation here at the left, change in the line position can be related to the pH. In the middle, signal width can be related with PO2. And at the right, the change in the amplitude can be related with the redox status. Therefore, in order to visualize them, it was necessary to develop a technique enabling the reconstruction of the spectra for the individual voxels of the image. At the left, authors shows the feasibility of the approach using the convoluted back projection algorithm that require data collected over 180 degrees. Algorithms are also available to reconstruct the images when the data can only be obtained over a limited range of angles. This missing angles algorithm can be used to extend this approach to case with the larger spectra width to the smaller values of L, this L is in centimeter, for a given gradient and the spectral width. At the right, in 1987, Eaton proposed the three-dimensional EPR imaging with one spectral and two spatial dimensions. As image was displayed as a two-dimensional spatial maps of the spin density of the EPR spectra, intensity at the particular value of the magnetic field. The spectral dimension gives the hyperfine split EPR spectrum at each point in the spatial plane. An electron paramagnetic resonance image was measured for the first time from the in vivo field gradient spectra of the living marine tumor using the paramagnetic nitro oxide imaging agent injected into the tile vein. The experiments were accomplished at the L-band frequency spectrometer using 1.55 GHz with a single-tone flat loop coil. A cross-section image was obtained perpendicular to the tail axis, which clearly distinguished the features to the sub-millimeter resolution level. In 1990, the authors discussed the mechanism of clearance of nitro oxide radicals in whole mice. In the in vivo measurement of nitro oxide radicals in whole mouse was carried out using, again, L-band EPR spectrometry. Spectra were successfully observed in hepatic and the bladder domains of the female mice after intravenous administration of the spin label compound. And this compound could be, for example, tempo. The signal intensities from the both domains decrease gradually. The clearance constants in the bladder domain coincident with those in the hepatic domain. This study shows that the use of EPR provides an opportunity to gain the new insight into the spatial distribution of the free radicals in selected region of the rat at different times. It was the first dynamic investigation of the EPR of the rat's organs. Three-dimensional spectral spatial image were obtained from the isolated, perfused rabbit aorts and rat hearts. It has been hypothesized that the free radicals metabolism and oxygenation in living organs and tissue, such as heart, may vary over the spatially defined tissue structure. In effort to study these spatial defined differences, the author have developed electron paramagnetic resonance imaging instrumentation, enabling to performance three-dimensional spectra spatial images of free radicals infused into the heart and large vessel. The effect of fascin, a new agent for the measurement of the concentration of oxygen in vivo EPR or MRI image, have been studied in the presented publication. The EPR spectra of fascin in the tumor were obtained using a commercially available those days Varian A9 EPR spectrometer and a homemade microwave bridge operating at L-band 1.1 gigahertz. Authors concluded that the in vivo EPR oximetry in conjunction with MRI makes possible repeated non-invasive measurements of the intratumoral PO2 as a function of tumor size, stage of growth, and the region of the tumor. Ongoing experiments are utilizing these techniques to measure intratumor PO2 in marine tumor under the condition when a more complete understanding of oxygen dependence process should translate into the improved cancer therapy in future. In 1994, Halpern groups present the measurement of the oxygen concentration in the body water of marine FSA and NFSA fibrosarcomas using the new method for quantitative oxygen concentration determination deep in the tissue of the living animal. The measurement uses unusually low frequency electron paramagnetic resonance spectroscopy with the sensitive to substrate 7 centimeter deep in the tissue. They quantitatively measured with the minimal tissue invasion, oxygen concentration in the body water, compartment of the marine fibrosarcoma implanted into the mouse leg. The spectrometer's operational frequency was 250 megahertz. Thanks to this, electromagnetic wave penetration increases up to 7 centimeters. At width, deep human tissue became more accessible to the EPR measurement. EPR can be useful not only for the biological domain. The Kruchawa study has demonstrated the potential of imaging methods based on EPR to provide the details of the polymer degradation and stabilization that cannot be deduced from the properties averaged over the entire sample. The nitro oxide in the butadiene-rich domain is consumed rapidly on the irradiated site and decreased to zero after 934 hours of the irradiation. On the non-irradiated side, the degradation is much lower. But even on this side, a discrete percentage of the fast components is detected when the irradiation time increases from 131 hours up to 934 hours. This work presents a methodology for obtaining the quantitative oxygen concentration images in the tumor-bearing legs of the living T3H mice. The method uses high-resolution electron paramagnetic resonance imaging. Enabling aspects of the methodology include the use of the injectable narrow single-line spin probes and an accuracy model of the overmodulated spectra. Both of these increase the signal-to-noise ratio, resulting in the high resolution in the space. It was around 1 millimeter volume and the oxygen concentration about 3 torr. Images were obtained at 250 megahertz spectrometer with a loop gap resonator consisting a cylindrical inductive sample holding element. The loaded quality factor, Q, of the resonator was measured at once the mouse tumor was installed. These images presented in the paper were the first fully three-dimensional spatial dimensional correlation between the bold MRI, and the EPR. EPR spectra of the suspension of LIPC, microcrystals, and von Wiehr aortic cells were collected from up to 160 minutes. As the time increased, the EPR line width decreased due to a concentration depletion of oxygen by the cells, as shown in the left picture. The spectra were collected until line width reached a constant low value. It was confirmed that the oxygen consumption measurement by the EPR oximetry is essentially due to mitochondrial respiration. The EPR spectra were analyzed and transformed into PO2 versus time data using the standard calibration curve. Two obtained results are presented on the right picture as the function of time for these different cells densities. In each of the cells density plots, there are three distinctly different regions, namely we have a linear portion, a curved portion, and the region with no change in PO2 with the time. Electron paramagnetic resonance imaging has emerged as the promising non-invasive technology to dynamically image tissue oxygenation, owing to its extremely short spin-spin relaxation time. Electron paramagnetic resonance imaging benefits from a single-point imaging scheme where the entire free induction decay signal is captured using the pure phase encoding. The combined application of gridding and decay space extrapolation enables the pixel-wise quantification of T2 star from a single acquisition with the improved image quality across the wide range of phase encoding time delays. The calculated T2 to PO2 does not vary across this time range. Cyclically ordered phase sequence, called Cyclops, was implemented to correct for the poles, imperfections, and cancel out unwanted constant signal. These upgrades considerably enhanced the performance of the imager in the terms of image collection time, sensitivity, and the temporal resolution of the whole system. Radiation therapy is one of the main modalities to treat the cancer. The response to radiation therapy can be influenced by the physiological condition in the target tissue, especially by the low partial oxygen pressure and altered redox status in tumor tissue. Tumor hypoxia could be seen by the position emission tomography (PAT), Electron Paramagnetic Resonance EPR oxygen mapping, and the in vivo dynamic nuclear polarization DNP MRI. At the right, we have the study served as a proof of concept of multimodal oxygen imaging in developing an algorithm to make PAT more comparable with the quantitative EPR partial oxygen pressure imaging in the terms of enabling location of tumor hypoxia in incorporating dynamic contrast enhancement MRI. In conclusion, using the EPR information as a reference standard, MRI information can be used to correct the PAT information to more accurate reflex across areas of hypoxia. One of the major values of knowing the distribution of oxygen tension in the animal tumor is the insight that it gives into the distribution of the radiation dose that should be administration to optimally treat a tumor. According to the authors, the current practice of maintaining dose homogeneity over the tumor volume is statement of ignorance as the spatial variation of the radiation sensitivity within the tumor. In future, the quantitative non-invasive EPR or PO2 images of the human tumor and local oxygenation statistic within the tumor might allow targeting dose modification to improve the local control. For the experiment, authors used 250 MHz pulse imager with a new transmit-receive switch used there to enabling 1 kilowatt peak-to-peak pulse power operational with a reflection resonator. At the right, the article presents the experimental demonstration that the EPR oxygen image guided radiation therapy increased the tumor control with the hypoxic boost doses relative to the well-oxygenated tumor boosts of the roughly the same volume in the mouse fibrosarcoma models. This was the first demonstration of the effectiveness of targeting specific hypoxic tumor in the mammalian systems. The application of EPR to melanins has led to many discoveries concerning melanin structure and melanoma development. EPR spectrometry approved as a unique tool to identify the ultraviolet range responsible of melanoma causing and help to resolve the controversy. The consequences of this demonstration will be very important in the field of sunscreen development, which should undoubtedly contribute to reduction of the melanoma prevalence. In vivo EPR measurement of the radiation inducted change in the enamel of teeth is a method useful for the classification in individuals into the categories for the treatment with sufficient accuracy to facilitate decision on the medical treatment. In this current state, the in vivo EPR dosimeter can provide estimation and estimated of the absorbed dose with an error approximately plus minus 50 centigrades over the range of interest for the accurate biological effects of radiation, assuming repeated measurement of the tooth in the mouth of the subject. Here, authors postulated a key role of the tumor microenvironment in cancer progression, treatment resistance, and the target for the therapeutic intravenous in the increasing appreciate. Among important physiological components of the tumor microenvironment are the tissue hypoxia, acidosis, elevated concentration of the intracellular glutamine, and anorganic phosphorate. Non-invasive in vivo measurement of the mentioned parameters and redox assumed to provide unique insight into the biological process in the tumor microenvironment. The recent progress in EPR instrumentation designated to be used in human and the development of the biocompatible paramagnetic probes with the spectral sensitivity to the parameters of the local chemical microenvironment. Potentially, it will make possible the transition of the EPR techniques for multifunctional profiling of the tumor microenvironment into the clinical settings. This technique will allow improving prediction power of the early diagnostic for malignant transition and future design of the anti-cancer therapeutics. The question is, do we need a whole body ERI scanner? If not, why we have the whole body MRI? The answer is because the living organism consists of many interrelated organs. Because we finally would like to use it for examining a patient and find the dysfunctions in a place that we do not expect or we do not expect it before. There are many obvious advantages and much more not yet discovered. We describe the perfect tool properties for animal researchers and we put it into the short list. Then we spent many years to meet all of them. Our system is ready to operate, easy to maintain, mouse whole body access. We examined 35 grams mouse, fast self-tuning, almost in real time, quick measurement. We got a single projection in the milliseconds or less, simple image reconstruction, friendly software, and we called the system ERI. And the ERI tomography is based on electron paramagnetic resonance phenomenon in which the source of the signal are subsequently constrained on unpaired electrons, such as free radicals, transition metals, or in the case of the in vivo test, spin probes administered to the body. Apart from the simple distribution of the spin probe in the animal body, it is possible to obtain the spectral information that reflects the parameters of the tissue microenvironment, including, for example, redox state, oxygen concentration, oxidative stress factor, like the concentration of thiols, and recently pH and inorganic phosphorus. Measurement became more and more possible. ERI technique is based on magnetic resonance imaging, but due to a complicity different signal source, it cannot be directly compared with MRI technique. However, we try imaging the same object using both technique. The phantom at the right consists the 3 small bottles filled with the aqueous solution of the tritol with a different concentration of the spin probe. It was possible to obtain an identical spatial image with comparing with the clinical 3 Tesla MRI system. In the picture on the right side, you can see that the ERI technique allows observing the differences between the concentration, which was not directly visible in the MRI technique. Also, despite the use of much lower magnetic field, it is possible to obtain the high-resolution images, such a cross-section of the object visible in the middle part of the slide. As I mentioned before, ERI tomography cannot be used for the typical anatomical imaging. However, the possibility of obtaining high-resolution image, it is possible to get the information about the anatomical structure. To prove it, we perform an experiment in which we put a mouse skull in the vial with the spin probe. By imaging and negating the obtained image, we managed to reconstruct the structure of the skull. The resolution of the classical EPR technique depends on width and EPR signal and the applied magnetic field gradient. However, when using the single point imaging technique, it is possible to improve the spatial resolution over 10 times. The in vivo ERI requires administration of the paramagnetic substances called the spin probes into the animal body. There are 2 types of the spin probes. We got a soluble and insoluble. Particles of the spin probes are usually implemented into different parts of the body, allows for the local measurement of the EPR signal. The main paramagnetic substances using for this purpose is LIPC. This type of measurement is currently used in the clinical trials in the form of the biocompatible particle called oxychip or micro-oxychip. However, liquid spin probe are more suitable for the imaging. We can distinguish 2 types of the soluble spin probes: the tritols, which allow to imaging oxygen concentration, and the nitrooxide, which is very useful for imaging the redox state. These days, the research is focused on increasing the effectiveness of functionality of soluble spin probes. Those probes have a big potential due to their properties, such as accumulating in the specific localization of the body, for example, tumor cells. They can also penetrate the cells or cross the blood-brain barrier. As I mentioned before, one of the unique properties of the ERI imaging is monitoring the reactive oxygen species, ROS, which are constantly generated in the living cells as a side product of oxidative metabolism. The demanding effect on cells components is determined by the rate of the generation of the ROS and the concentration of low molecular weight antioxidants together with their enzymes activity. Factors increasing the rate of ROS generation is, for example, ionizing radiation or the metal ions, as well as facts decreasing antioxidants capacity leads to oxidative stress, causing the enhancement oxidative damage of the cellular components. So, we can describe oxidative stress as an imbalance between the production of the free radicals and the ability of the body to neutralize or detoxify their harmful effects, which is defined as a redox state. What is important? The stronger oxidative stress produces the greater change in the redox state. Interesting fact is that the recent publications indicate that oxidative stress plays an important role in the SARS-CoV-2 infections. Now, I would like to show the differences between the ERI technique and the other imaging modalities such as MRI, PAT, or CT. A unique property of ERI is the ability to mapping the oxygen concentration, redox state, and acidity in the tissue in the in vivo experiments. Those parameters cannot be measured by the other techniques. For example, in MRI and PAT, the oxygen level is always measured indirectly, or by the blood saturation in bold MRI, or presence of hypoxic region in the PAT. Redox state is based on the free radical mechanism rather than the typical image concentration enhancement. pH or PI maps can also provide unique parameters, especially for the tumor microenvironment. Lack of ionizing radiation does not require an additional control group to eliminate the radiation impact. All this makes ERI a powerful and constantly enveloping technique with a great scientific potential. Thank you very much for your attention.
Please follow us on the Facebook and LinkedIn. Have a great day. Goodbye.